Control-oriented modeling of buildings is notoriously challenging because of several sources of heat transfer, but overall limited sensing. On the figure to the left, you'll see several unmeasured time-varying heat gains on a building space, as well as unmeasured states associated with the building mass thermodynamics. In this work, we develop a gray box model with an integrated disturbance forecasting model. Specifically, we consider a very standard building space thermodynamic model with two states. It has a state associated with the indoor air temperature, as well as a state associated with the lumped building mass temperature. So what we do is we parameterize this model. This results in 5 system parameters, as well as 2 parameters associated with the initial states. We replace the unmeasured heat gains with a neural network model to be able to predict the heat gains. And we model this neural network with the following input features: time of day, day of week, and day of year, which these variables would be correlated to the heat gains for a standard commercial office building. In the paper, we present 2 methods for training this model, but I will present the results for one of those approaches. In particular, I'm showing here a 2-day prediction using the training data set. And what we see is we get very good results, very close accuracy of the predicted temperatures and this heat gains with respect to the actual. If I do a similar 2-day prediction over a validation data set, a data set that I did not use for training, what I see is over the first 18 hours, the predicted temperature is very close to the actual. However, after the 18 hours, we can see noticeable errors associated with the predicted versus the actual. This is mainly due to the fact that I've used a very limited data set in my training. So while I'm able to get good system parameters, I'm not able to train the neural network very well. However, because the overall modeling framework is non-monolithic, what I can do is use the system parameters as well as a disturbance estimator to estimate the disturbance over time as I collect more data, and then use this estimate to update the neural network model. I encourage everyone to check out our paper on this subject, and I appreciate everybody's time.
Hello everyone, my name is Max Schüssler. I'm a research associate with the research group Automatic Control Mechatronics from the University of Siegen, and I want to give you an overview of our paper, Optimization Approaches for Nonlinear State Space Models. This paper is published in the IEEE Control Systems Letters. It is authored by Professor Oliver Nellis and myself, and I am also the corresponding author. Our field of research is nonlinear black box system identification, and we developed an identification algorithm which is based on the nonlinear state space model shown here on the left. And what we do for the approximation of the nonlinear state and output equations is that we employ local model networks. We call this model the local model state space networks. We employ the local linear model tree algorithm to iteratively increase the complexity of the local model network. One obstacle we currently face are long computation times of the currently employed quasi-Newton optimizer, and to make use of some developments from the machine learning community, we wanted to use the adaptive moment estimation optimizer, short ADAM, for our nonlinear state space model for faster convergence. And now I skip all the details and refer you as the surely interested listener to our poster and paper and come right to 2 of our results. In a first study, we investigated a first-order Hammerstein process, which can be seen in the blue bar on the top. All shown root mean square error values are simulation errors. To the left are 4 plots which indicate with the different colors different stages of our LMSSN model training when more and more local models are added for increased complexity. And those are shown in the larger plots for models trained with ADAM, plotted for different mini-batch sizes on the x-axis, and 4 different plots show the results for different base learning rates. The small strips on the right side of the 4 plots show the quasi-Newton optimizer results, And when we compare the blue lines, we can see that the best learning rate increases with the batch size, and this effect wears off with the increasing number of splits. This is consistent with a linear scaling rule that the number of samples per mini-batch is proportional to the learning rate eta. A second result I want to show you has been obtained from a Wiener-Hammerstein benchmark. We trained LMSSN models with quasi-Newton. This was done on a single batch, and it led to low parameter variance and no hyperparameter tuning is necessary. On the other hand, when we trained models with Adam with mini-batches, this led to a 30 times faster convergence, but comes at the cost of higher parameter variance and tedious hyperparameter tuning. Thank you for your attention. For more details, take a look at our poster and paper. And if you have any questions, feel free to contact me anytime. Bye.
Hello, I'm Juan Paredes from the University of Michigan, and today I will talk about identification of self-excited systems using discrete time delay Lure models. Self-excited systems have an asymptotically oscillatory response to a constant input. These are applicable in thermoacoustics, chemistry, biochemistry, fluid structure interactions, among others. A classical example that displays this behavior is the van der Pol oscillator. S will denote a self-excited system, and M will denote a discrete time model whose structure is designed to capture the self-excited dynamics of S. M is chosen to be a discrete time delay Lure model. The DTTDL model incorporates an asymptotically stable and strictly proper plant G, a time delay GD, a washout filter GF, a nonlinear function N, and a bias generation mechanism, arranged to form the positive feedback system shown in the block diagram. The nonlinearity N is assumed to be continuous piecewise linear. As such, we can define a domain partition represented by vector C, the slope vector mu, corresponding to the slope in each partition interval, kappa, which determines the range offset, and function nu. This allows us to write the nonlinearity in a compact form. In the case where the nonlinearity N of the DTTDL is CPL, the model output can be represented as the dot product of parameter vector theta and measurement vector phi. The technique depends on choosing values for order n, delay d, and partition vector c, such that phi is known. Hence, the objective is to estimate parameters encoded in theta. For this purpose, we first define the least squares cost j that represents the difference between the measured output and the output from the current model. The strategy is then to minimize the upper bound of j by sequentially minimizing jls and ja, which require minimization via linear least squares, an arbitrary choice of beta, since b and beta are unidentifiable from theta lambda, and the minimization of ja. A numerical example is now shown, where the nonlinear estimation algorithm was used to obtain a DTTDL CPL model that captured the dynamics of a van der Pol system whose measured output had an added bias. In conclusion, this paper developed a technique for identifying self-excited systems based on discrete time delay Lure models with continuous piecewise linear nonlinearities. By minimizing the upper bound of a non-quadratic cost function, linear least squares techniques were used for parameter estimation. The numerical example shows the ability of the model to reproduce the limit cycle response of a van der Pol oscillator. However, the extent to which the DTTDL CPL models can approximate the response of an arbitrary SES is yet to be determined. Thank you for listening, and come to the interactive session if you want to learn more.
Hello everyone, thanks for your interest in the paper titled EM-based algorithms for single particle tracking of Ornstein-Uhlenbeck motion from ACC camera data. What is single particle tracking? Well, in life sciences, single particle tracking is a powerful tool to get important information of biomolecules, such as the diffusing speed and stiffness. Suppose there is a particle of interest under the observation of microscope camera, and then we get sequences of images taken by camera. The type of camera considered in this work is the scientific CMOS camera. By taking the post-processed images as input, we aim to make joint localization and model parameter estimation. dx and dy are denoted as the diffusion coefficients. ax and ay are denoted as the stiffness coefficients, and we would like to estimate these unknown parameters. Under the EM-based framework, two representative methods are used. One is called UEM, where the U scheme includes unscented Kalman filter and unscented Rochtown stable smoother. The other one is called SMC-EM, where the SMC consists of particle filter and particle smoother. This video gives an example of motion model and measurement model. The top left picture shows the global trajectory driven by Ulstein-Uhlenbeck motion. The top right picture shows the observations captured by scientific CMOS camera. The bottom two pictures display the characteristics of the radar noise. The scientific CMOS camera brings pixel-dependent radar noise, which means the radar noise for each one pixel at each time t is different. Here are the partial results showing the estimation performance by different methods. In terms of parameter estimation, both methods return good estimation results. In terms of localization, the performance difference mainly depends on the size of Monte Carlo samples used in SMC-EM. With a large number of Monte Carlo samples, SMC-EM shows better localization performance, but with the sacrifice of heavier computation time. Regarding to the computation time, as we can see from this picture, the UEM shows obvious advantage in computational efficiency. In a nutshell, the main contribution of our work is as follows. First, we introduced two EM-based methods, SMC-EM and UEM. Second, we extended single particle tracking application to Ulstein-Uhlenbeck motion and scientific CMOS cameras. Then, we conducted quantitative comparison between SMC-EM and UEM through parametric investigations and intensive simulation work. Last, we discussed and analyzed their prospective advantages in estimation accuracy, computational complexity, and efficiency, as well as the impact of data length on estimation performance. Thank you so much for watching.
Hello, everybody. My name is David Patrizzi, and in this short presentation, I'll be going over our group's submission to ACC 2021. As many of you are aware, the growing use of unmanned aerial vehicles, and in particular drones, presents a growing airspace security concern to certain facilities. Some examples of which include airports, power plants, prisons, anywhere you don't want a drone flying overhead. The fear is that these intrusions may engage in destructive acts. They might extract sensitive information or just otherwise engage in disruptive behavior, like what we see in airports often. This motivates security researchers to consider methods by which airspace intrusions can be detected and even counteracted. Conventionally, radar is used to detect these kinds of threatening intrusions. The one problem is that birds often show up where a drone will, and that's because they tend to fly at the same velocity and at the same altitude as drones do. This itself forms a classification problem where birds must be distinguished from drones in order to enable effective security. Our solution, in contrast to those existing, is to take a more system theoretic approach. We model aerial intruders as inertial bodies, which employ negative feedback in order to maintain a constant speed in the presence of a noisy disturbance. Our intuition stems from the idea that a drone will more tightly regulate its velocity over the course of some trajectory than a bird will. This difference in flight profiles is what forms the basis of the hypothesis test underlying our detector. The maximum a posteriori detector, which is illustrated on the right in that scatter plot, is fundamentally a linear classifier in terms of the input autocorrelation. In addition to presenting the ideal detector, as a part of our work, we derive a method to compute the maximum a priori probability of error, the probability that a detection result is false, which in other words means the probability of error conditioned on the input. And we prove that the a priori probability of error approaches zero as the number of samples used increases. Critically, our work is unique in that we combine modeled physics together with a measurement data to obtain low overhead detectors with quantifiable performance. And that's all I have. Thank you.
Hello, I am Dr. Joel Rosenfeld, and I'm giving you this talk about the connections between Liouville operators and dynamic mode decomposition. We're going to use Liouville operators, and we're going to be using occupation kernels, and their combination will allow us to find a finite rank representation, which will allow us to model a dynamical system. So the goal is to start with a dynamical system that we've observed through a whole bunch of snapshots, and we'd like to build a model for this system using this data. And what we're going to do is we're going to apply it to spectral theory and finite rank representations of certain operators. A Liouville operator is an operator where we take an observable or a function in a Hilbert space, G, and we take its gradient and we multiply it by our nonlinear dynamics. But we have to make sure that this observable is actually in the domain of this operator. And when you have this domain, we get a closed operator, which means we have a well-defined adjoint. Turns out if we take a look at the function that represents integration after composition with a trajectory from our dynamical system through the inner product in the Hilbert space, and we'll call this function the occupation kernel corresponding to our trajectory, it turns out that this occupation kernel is in the domain of the adjoint of this Liouville operator. Moreover, the adjoint of this Liouville operator gives us the difference of two kernel functions centered at the various endpoints of that particular trajectory. So we're going to take the collection of the occupation kernels corresponding to our trajectory, and we'll call this set alpha. And then we take a span, and this is going to be the vector space that we're going to be operating over. Then what we do is we take this finite rank representation and we take its transpose, and then we use this as a substitute for the original Liouville operator. So what we're going to do is we're going to take an eigen decomposition. We're going to get some eigenfunctions out of this matrix. So eigenfunctions for the Liouville operator are going to satisfy this very particular property. So if you take this eigenfunction and you compose with a trajectory from your dynamical system, and then you take this time derivative, this is just the Liouville operator applied to our eigenfunction evaluated at the trajectory. And so then we know that the eigenfunction composed with the trajectory can now be written as e to the lambda t times the eigenfunction evaluated at the initial point. What we do next is we take the identity function, or the full state observable inside of our Hilbert space, and we're going to take the projection of that full state observable onto our basis. Then if we take a state from our dynamical system, x of t, we now have a model for our dynamics where we take those eigenfunctions and we can replace it with this dynamic equation that we showed before. So now we have our state described as, say, an infinite series of our exponentials, and in the case of the finite rank representation, we replace this with an approximation where we now have x of t described in terms of a finite number of exponentials. What I described really just sounds like a whole bunch of one-dimensional stuff. You just do the same process for each dimension, and then you stack them together, and then it turns out that the weights are now vector valued, and these are what we call Liouville modes. And so that's how you do dynamic mode decomposition with occupation kernels and Liouville operators. So thanks for watching, and I'll see you next time.
Welcome to my short presentation on dispertivity verification for polynomial systems from noisy input state data. My name is Tim Martin, and this is a joint work with my PhD supervisor Frank Algeber. This work is motivated as follows. Dispertivity properties such as L2 gain give insight to the system and facilitate a controller design with closed-loop guarantees. However, usually verifying dispertivity properties requires the identification of a precise model, which is often time-consuming and requires expert knowledge on the variety of system identification techniques. Moreover, since the derived model doesn't describe the system exactly, we lose guarantees for the controller. Hence, to circumvent the identification step, we want to verify dispertivity properties directly from noisy input state measurements of the system, where we include information on the noise to provide end-to-end guarantees for the system properties and the controller. To have a closer look on the main idea of the approach, we consider the following problem setup. So we consider an unknown polynomial system. We suppose some insight into the system, namely that a vector Z is known that contains at least all monomials of the system dynamics, such that we can write the system dynamics as here, where the coefficient matrix A is unknown. Note that the knowledge on Z is not too restrictive, as Z could contain a large number of monomials. Moreover, we assume that some noisy input state measurements are accessible, where the noise vector is bounded either pointwise in each time step or by such an energy bound. I should emphasize here that the noise vector is not known. Using this information, we can conclude on the set of all systems feasible with the data. This set then of course contains the ground truth system. Hence, if we verify dispertivity for all systems of the feasible system set, we can conclude on the dispertivity of the ground truth system with guarantees. From this idea, we can derive sum of squares and LMI conditions to verify dissipativity by a generalized S procedure. To conclude our contributions, we propose a framework to check whether a polynomial system is dissipative from noisy data following a set membership approach. We don't need to identify a model of the system and derive guaranteed inference on dissipativity properties of the ground truth system. In case of questions, you can come to my poster during the poster session, or you can write me an email.
My name is Arash Komai, and this is a work with my graduate student Terry Ann Sneed. The problem is reconstruction of vector fields from noisy observations of their flow curves. The problem is motivated by this experiment. The goal is to construct a magnetic force field from the observations of generated by this testbed. In this testbed, we have a flat tray which is filled with a highly viscous fluid in which a magnetic bead can freely move toward a magnet on the edge, and a camera is on the top to record the trajectories of motion starting from different points on the tray. The equations of motion of this system is given here, which is a ordinary differential equation with an unknown right-hand side. And the goal is to estimate the right-hand side of this differential equation, which is a vector field, based on the trajectories of motion observed by the camera. The problem is formulated as we have a differential equation with some initial state, and we have the noisy observations of the trajectory of this differential equation at certain sampling points. And the question is how to estimate the trajectory x and the vector field f along this trajectory based on this noisy observation. The problem is formulated in the form of a least squares problem, and a linear quadratic tracking framework has been used, in which the goal is to make a trade-off between smoothness and goodness of fit of the estimated trajectories. After solving the formulated problem using the known results in linear quadratic tracking problem, we have a bundle of estimated trajectories and estimates of the vector field along these trajectories. Then using a k-nearest neighbor interpolation, we can construct the magnetic force at the points which are not on the estimated curves. Here is some results of our experiment and computation, which includes a typical estimated trajectory for position and velocity. We have the amplitude of the magnetic force estimated, and we have the phase of magnetic force. And also we have a color-coded construction of the magnetic force, including the trajectories from which the magnetic force is estimated. Thank you.
Hello, my name is Adnan Saoud, and today I will be presenting a robust hybrid finite time parameter estimator. So we have a linear regression model where y represents the known output, phi the known regressor, and theta star is the constant unknown parameter we want to identify. So in order to estimate theta star, we use the classical gradient descent algorithm. Indeed, we define a parameter estimator theta, to which we associate an update law described by the following differential equation. And then it can be shown that if the regressor phi is persistently exciting in the sense that it satisfies this condition, then the parameter estimate theta will converge to theta star asymptotically. So in this work, we propose a hybrid finite time parameter estimator. So the estimator is described as a hybrid system. The state of the system is made of two parameter estimates, theta 1 and theta 2, and the timer tau. The flow and the jump sets C and D are constructed in order to trigger a jump whenever the timer tau is equal to delta, where delta is a predefined positive constant. The flow map here is made of two copies of the classical gradient descent algorithm with different adaptation rates, gamma 1 and gamma 2. And finally, the jump map is constructed based on the functionals K1 and K2 defined here, which makes it possible to ensure a parameter convergence at time delta. So we have here our main result. So if gamma 1 is different from gamma 2, and if the register phi is exciting over the time interval 0 delta, then the parameter estimates theta 1 and theta 2 will converge to theta star after the first jump. So the main characteristics of our parameter estimator are the following. So first, it allows for finite time convergence and the relaxed interval excitation condition. Second, it makes it possible to deal with constant and piecewise constant unknown parameters. And finally, the fact that it's robust with respect to bounded time varying measurement noise. So we have here a numerical example. So consider a linear regression model where the regressor phi is only exciting over the time interval 0, 1. And we can see here on the figure that the parameter estimation error will converge to 0 within 1 second. And moreover, we can also see the robustness of our hybrid parameter estimator with respect to a noise of the following form. And thank you for your attention.
Hello everyone, thank you for your time today and welcome to my presentation on UAV state and parameter estimation in wind using calibration trajectories optimized for observability. My name is Animesh Shastri and I am working as a research assistant under the guidance of Dr. Derek Bailey at the University of Maryland. The motivation for this research comes from the lack of capabilities that the traditional linear system identification method provides. For most aerial vehicles, including quadrotors, this involves flying in hover using an already stable controller and then recording response to chirp frequency inputs. Hence, we have developed an online recursive system identification framework that improves robustness and adaptability to different vehicle classes and payloads without the need for manual tuning. A block diagram representation for the online nonlinear system identification framework is shown here. The estimator updates the model using the biased sensor data corrupted by noise. The model, which is an actively updated, is also being utilized by a controller to minimize tracking error. The controller is nonlinear and is modified to include aerodynamic forces and moments. The process model contains the orientation, the vehicle's velocity, angular velocity, wind, drag coefficient, center of pressure, and the IMU bias. The measurement model contains the biased acceleration, biased angular velocity, and ground velocity measurements. The system has weak observability and thus we need a calibration trajectory that is optimized such that observability is as high as possible without too much control efforts. We used a superimposition of two Lysergis trajectories and minimized the unobservability index as well as the control efforts to improve the system identification as well as the controller's performance. During calibration, we are simulating an unsteady wind by the expression on the top left. Between the optimized and a manually selected trajectory, the latter one has lower observability, higher condition number, and also needs higher control efforts to track it. Hence, in the figure on the right, we can see that the red curves have higher errors in tracking as well as estimation. Also, the framework's chances of failure is approximately 92% with the manual trajectory and 4% with the optimized trajectory. In short, with the help of optimization, we are not only getting a performance boost, but also a huge increase in numerical stability. After 2 minutes execution of the self-calibration process, the framework can successfully estimate and reject very high unsteady winds as shown in the step response and position hold plot. Wind estimation plot is also shown on the right. Thank you for attending my presentation.
Hello, my name is Brian Lai, and I'm currently a PhD student at the University of Michigan. This work was done in collaboration with Asim, who is a postdoc at the University of Michigan, and our advisor, Professor Bernstein. This work studies the effect of regularization-induced bias on recursive least squares. Recursive least squares, or RLS, is a commonly used algorithm for real-time parameter estimation. When implementing RLS, the parameter estimate experiences bias from two main sources. The first is signal noise, and the second is regularization, which is necessary in startup as the least squares problem is ill-posed with insufficient data. The goal of this work is to isolate and study the effect of regularization-induced bias on recursive least squares. Under a persistently exciting signal, RLS is guaranteed to asymptotically converge. The speed of convergence varies depending on what biases are present. In the presence of noise and without regularization, RLS converges at order k inverse. In the presence of both noise and regularization, RLS converges slower, namely at order k to the power minus half. We showed that without noise and experiencing only regularization-induced bias, RLS converges at order k inverse. In addition, we will give an explicit expression for its asymptotic behavior. Here we provide an overview of the RLS problem formulation. Consider a discrete time linear measurement process where yk is the measurement at time k, phi k is the regressor at time k, and theta are the unknown parameters we are interested in estimating. Define capital YK to be the collective measurements and capital phi k to be the collective regressors. Denote theta k to be the minimizer of the regularized least squares problem at time k, where R is the regularization matrix. RLS provides recursive update equations to evaluate theta k at each time k. The sequence of regressors is persistently exciting if and only if the matrix C, defined by this limit, exists and is positive definite. In this case, this equation gives an explicit form for the asymptotic behavior of the regularized RLS problem. As shown in the asymptotes in the figure, the convergence rate is k inverse. Additionally, it's often of interest to predict the performance of RLS soon after the least squares problem becomes well posed. The asymptotic behavior gives an approximation for this performance. Thank you for your time, and I look forward to discussing this paper further with you at the upcoming interactive session.
My name is Elliot Skomsky. I'm a data scientist with the Applied Statistics and Computational Modeling Group at Pacific Northwest National Laboratory. And this is a quick overview of our paper, Constrained Block Nonlinear Neural Dynamical Models, co-authored by myself, Samya Vasisht, Colby White, Aaron Tour, Jan Dragona, and Draguna Vrabi. This work is motivated by the broad applicability of dynamical systems modeling and deep learning, and the challenge of combining the two. Notably, although deep learning represents a powerful class of models capable of approximating complex functions, it isn't known for being particularly effective in small data regimes, nor does it provide stability or operational safety guarantees on its own. To this end, we set out to develop data-efficient and stable deep models of dynamical systems, which we accomplish via a block-oriented neural model structure, the use of structured linear map priors, and optimization constraints. In this work, we focus on partially observable non-autonomous systems, which we can formulate as deep models in a couple ways. Perhaps the simplest approach is to use a single neural network which jointly learns the state transition dynamics and control input interactions. This is our unstructured neural model. This is a serviceable solution for highly nonlinear systems, but applying physical priors to this formulation isn't as straightforward. So to address that, we propose an alternative formulation, block nonlinear dynamical models, which separate state transition dynamics and control input interactions into separate nonlinear functions and combines them explicitly with addition. This simple transformation gives us additional flexibility to apply separate priors to the structure of each model component and directly define the interactions between state and control input. You might notice the resemblance between this model structure and that of traditional block-oriented state space models. Finally, since we're working with partially observable systems, for both models we use an additional neural network to generate initial states from past observables. Using this generic block-oriented model framework, we can now begin to embed physical intuition about dynamical systems into models, using structured linear maps to induce sparsity or spectral constraints in various model components, and by including penalty functions in our training objective to bound the output of the model, limit the effects of control input on state dynamics, and so on. Experiments using 3 dynamical systems demonstrate the broad efficacy of applying constraints to neural dynamical models, with considerable improvements in open-loop performance for each system. Using block structure proved itself useful for systems with simple interactions between control inputs and system state, while unstructured models appeared to be more appropriate for systems with complex controls. Overall, we demonstrate that some general intuition about underlying system dynamics can be leveraged to design more effective and stable models with less data, and that block nonlinear neural state space models, combined with structured linear maps and optimization constraints, can flexibly model a wide range of nonlinear dynamical systems. Thank you for watching.
Hello, and welcome to my talk. I am Dr. Joel A. Rosenfeld, and I'm here to talk to you about a new system identification method that my colleague and I have put together for the analysis of nonlinear dynamical systems that are fractional order. This is all going to be living inside of a Hilbert space of some kind, and so we're going to be talking about reproducing kernel Hilbert spaces, and we're going to be talking about these particular functionals that arise from what are called occupation kernels. If we take a function g from our Hilbert space, and we take a trajectory satisfying our fractional order dynamics, we can take a look at that functional where you do the fractional integral of g composed with these fractional order dynamics. If g was replaced with the dynamical system itself, then basically we're doing an equivalent version of the fundamental theorem of calculus, but for fractional order systems, and so now you get the difference of f at two different endpoints. What's interesting is that we can take this functional and show that it is bounded, and so there is actually a function that lives in our reproduced kernel Hilbert space that represents this functional. So we call this a fractional order occupation kernel. Now, what's interesting is that if we want to approximate the dynamical system and we have a collection of trajectories that satisfy the dynamical system, what we can do is we can pose this as a regularized regression problem where we take a look at the sum from I going from 1 up to m, where m is the number of trajectories we have, and we take a look at this quantity squared where we have the fractional integral of f of one of our trajectories is equal to the difference of the endpoints of our particular trajectory. Now, if this is an n-dimensional problem, we'll just do this approximation one dimension at a time. And then what we do is we regularize the problem just by adding lambda times the norm of f squared. And so if we want to minimize over all f inside of our Hilbert space, we can use the representer theorem and demonstrate that f has to be a linear combination of these fractional order occupation kernels that we started with. And so then we plug that back into our system. Then we have a finite dimensional optimization problem to solve. Take the gradient of this problem, set it equal to 0, and then you get this very nice form where you have the sum from I going from 1 up to m of this vector vi times vi transposed, where vi is a column of inner products of these occupation kernels plus lambda times the gram matrix of this basis. And then we take that whole matrix and we take its inverse and apply that against the gram matrix times this vector that we have of the difference of endpoints of the various trajectories. Then this gives us the weights that we need to put onto our occupation kernels that give us the approximation of our nonlinear fractional order dynamical system. And it turns out that this works out really well. I should say that this is not only new for nonlinear fractional order systems, but it's also a new technique for the study of regular dynamical systems. So if you'd like to learn more about this, you can check out my YouTube channel where I have an extended discussion about this technique, and there I have some code that I can share with you. Thank you for watching, and yeah, I'll see you next time.
Hello everyone, I'm Xu Dading from Shanghai Jiao Tong University, China, working with Professor Jianping He, Cai Linchen, and Xinping Guan. Today, I will present a system parameter and state estimator over nonlinear systems. Estimators are used to acquire system dynamic model structure, parameters, and states, and provide basic knowledge for the controller design. Estimators have broad applications, such as topology inference, focus, adaptive control, and optimization. The existing methods including system identifications, adaptive observer design, and data-driven modeling. They are based on operation data, however, they have limitations, such as model type selection, model order selection, and providing estimation bounds. So these limitations cause difficulties in applications. We discovered potentials to solve these issues. However, we still face challenges in this work. The system is unknown. Error bound need to be determined. In this work, we design an estimator with error bound over an unknown linear system. Also, in this work, the idea of learning methods plus feedback control provides preliminary estimation, and the design procedure to improve accuracy. Estimation error bound are shown in past expression. The SISO LTI system is given with the following assumptions. We introduce Lomberger state observer and the SVR to construct the estimator. The goal is estimating parameters, acquiring regression error, guaranteeing stability, and improving the accuracy. Now we introduce the main results. The estimator structure is shown in figure 3. Theorem 1 gives the ratio error bound and shows the accuracy increase with the number of the input data. Then we have the error bounds of every element in matrix A. Theorem 2 provides the design to guarantee the stability of estimator. The states are with BIBO stability. Finally, the procedure bases on the bias of output and estimated output to adjust the estimator. We designed numerical experiments to verify the proposed estimator. As we can see, the estimation without adjustment procedure still have errors on state estimation, and the adjustment reduces the error and guarantee the performance. Also, parameters in matrix A are precisely estimated in the end. Now we conclude this work. The state matrix is regressed by SVR. Regression error is determined by mathematical analysis. The observer gain is assigned based on the regression error and guarantees the BIBO stability. A procedure is proposed to adjust the matrix and reduce the error of the estimations. The numerical simulation further verify the design. This work is not enough. In the future, we still need to consider a tighter bound for parameter estimation and apply to a nonlinear system by reducing kernel function into SVR. Thank you.
Hello everyone, my name is Yu Xuan. I'm a PhD student at Clemson University. My advisor is Dr. Mohammed Magnian. Our research is about attack detection and identification for cyber-physical systems utilizing generalized Limburger observer. As shown in the left figure, a cyber-physical system consists of two network layers, the physical layer and the cyber layer. Either inside a layer or between layers, the interactions are often accompanied by delays. Furthermore, those communication channels are under the risk of malicious attacks such as deception or false data injection attacks. Longitudinal vehicle platoon is one of the examples. It refers to the one-dimensional control of a sequence of vehicles along the direction of motion. It also provides a model of our simulation. In the platoon case, an attacker may hijack the actuator, sensors, and communication channels, which represents the cyber to physics, physics to cyber, and cyber to cyber interaction in cyber-physical systems. To be general, we developed the monitor scenarios for the linear time invariant systems with delays under attacks and disturbances to detect attacks and identify their locations. We extend the standard Limburger observer to a more general case termed as the generalized Limburger observer. They have the similar form. Its Limburger gain is a transfer function instead of a constant. We find that it is perfectly suitable for attack detection and identification scenarios. These scenarios are residual-based and model-based, and we assume that the bound of the exogenous disturbances or noises are known or could be well estimated. We first designed the generalized Limburger observer to estimate the residue of the monitored output, which is the difference between the estimated output and the measured output. Then we get the transfer function gain by solving a convex optimization model matching problem in frequency domain, which also provide a tight bound for the residue as a threshold to detect attacks. Then, based on the detector, identification is achieved by applying structural constraints on the mapping from pre-modeled attack signals to residues. Though our work is motivated by deception attacks, the algorithms can also be applied for DOS attacks or system faults. If you are interested in our work, please come to our live Q&A session and see our poster. The number is 965. Thank you.
My name is Daisuke Uchida, a graduate student at the University of Tokyo. In this paper, we propose a data-driven controller design based on the Koopman operator and extended H2 norm characterization. Consider a problem to control a nonlinear system given by the map F. Using the Koopman operator, which governs the evolution of so-called observable functions, we may represent the nonlinear dynamics in an infinite-dimensional function space. Further, based on numerical approximations of the Koopman operator, controllers can be designed in purely data-driven manners. However, data-driven models obtained in this framework may suffer from the model uncertainty which arises from its data-driven nature. In this paper, we propose a data-driven controller design that takes this model uncertainty into account. First, we construct multiple data-driven models from data. Variation of the system matrices of these models is considered as the model uncertainty that arises from some data-driven factors. We then interpolate its variation with a polytope set. The reason of interpolating with a polytope set is that we can make use of its convexity to formulate robust controller design in a simple way based on the robust control theory. Using this model, we then design a data-driven controller by solving the following problem. This formulation is based on the extended H2 norm condition of discrete time linear systems, and the obtained controller is robust to the model uncertainty arising from data-driven factors. Here are some numerical examples. As a problem setting, it is assumed that we have no access to the governing equations of system. Instead, we design controllers using measured data. The first example is the Duffing oscillator. As you can see here, the proposed controller makes the peak of the response lower than the other controllers, which do not take the model uncertainty into account. Here is another example of the KdV equation. In this case, the governing equation is a partial differential equation, while in the previous example, the system was governed by a simple two-dimensional state space model. As shown in these figures, the proposed controller regularizes the states efficiently, while the other ones have difficulty stabilizing the system.
Hi everyone, my name is Mona, and today I will present you our work on joint state and dynamics estimation with high-gain observers in Gaussian process models. So let's start with a little bit of context. Let's say you have a certain dynamical system you're interested in, for example the airflow around this car. You build a prior model of it, be it from first principles or using high-fidelity numerical simulations from which you learn a reduced-order model. Now, this prior model was long and difficult to design, but now that you have it, it's quick to evaluate and it can be very accurate. But let's say you take some measurements of the corresponding physical system and they're not quite what your prior model predicts. What if the physical system changed or if some effects were not modeled? Well, then we would like to update this model with on-site measurements, for which only partial data is available and which contain measurement noise. So the problem we tackle here is how can we enrich our prior model with this experimental data? Now, why is this difficult? Well, it combines two research problems. On the one hand, we have state estimation. We need to reconstitute a full state from these partial and noisy measurements, which is already its own research topic, and for which most state-of-the-art methods need an accurate model of the dynamics. And on the other hand, we need to learn part of the dynamics, which is also its own research topic, and for which full state data is usually needed. So how can we do both of these things at the same time? Well, what we propose to do here is to take this data that we measure on the physical system, feed it into an observer, which produces estimated state trajectories, and then use those to learn a model of the dynamics, which is then put back into the observer to make it more accurate. And we go into this cyclic motion until we have an accurate observer and an accurate dynamics model. And we also want to guarantee joint convergence of both the observer and the model. We assume that we are in the observable canonical form, which you can see here in 2 dimensions, and that we use Gaussian process models for learning. So we build a high-gain observer, which reconstitutes the full state from our measurements, and we'll learn a discrete dynamics model of the nonlinearity with a Gaussian process. Now, thanks to the robustness of the high-gain observer to model uncertainty, and to the smoothness of the Gaussian process model with respect to its data, we can show, in a certain sense, that we have joint convergence of both the estimated state to the true state and the estimated dynamics model to a true dynamics function. And we demonstrate this on numerical simulations. So to conclude, what our framework does is that it takes a prior dynamics model, some partial and noisy experimental data, and updates the model to adapt it to the physical system by jointly estimating the state and learning the dynamics. So if you want to know more about this, go ahead and ping me.
Hello, my name is Nicholas Vickers, and this paper is titled Tracking Multiple Diffusing Particles Using Information Optimal Control. In the study of biophysics, it is now common practice to track multiple particles in order to infer their behavior. Examples of this include tracking a virus particle to see how it enters a cell, tracking neurotransmitters to see how communication between neurons occurs, as well as tracking molecular motors to infer their mode of locomotion. The problem we consider in this paper is to track these multiple particles with a laser scanning confocal fluorescence microscope. The goal is to control the location of the laser focus in order to minimize the uncertainty of estimating the particle's location over time with a high temporal and spatial resolution. Our proposed solution consists of a two-level scheme. In the lower level, we use an extremum-seeking controller to track the particle, where its orbiting radius was set to maximize the Fisher information. We also show that this controller smoothly converges to an information optimal orbit when its initial position starts within a certain critical maximum radius from the particle. The higher level controller decides on which particle to track and the duration of tracking in order to minimize the worst case estimation error over long time horizons. We show the potential of this approach through simulations, where the trajectory of the laser iteratively visits each particle, and at each particle we switch to the lower level controller where it commences to orbit the particle while tracking it. Particle position estimation was done by applying a particle filter and a Rausch-Tung-Streibel smoother to the detected fluorescence intensity data. This resulted in a root mean square error of estimation of 100 nanometers with lower photon counts than conventional approaches. The performance of the high-level controller is shown through the graph on the bottom right of this slide, where the estimation error increases when the system is not observing a particular particle, where observation durations are indicated by a gray bar. While the microscope is observing a particular particle, the estimation error drops rapidly and stays at a low level. Thank you for your attention, and I look forward to discussions and answering questions at the live question and discussion session.
Hello everyone, my name is Shihong Wei. I'm currently a second-year PhD student in the Department of Applied Mathematics and Statistics at the Johns Hopkins University. This work is part of an ongoing project I'm working on with my advisor, Dr. James Spohr. We aim at developing methods to compute valid confidence intervals for the estimation error of a class of filtering algorithms in a scalar case, especially for nonlinear systems where the direct computation of the error distribution is usually untrackable. As we know, filtering algorithms estimate the state variable x given the observation measurement z up to the current time point. Our focus here is the error of the state estimation, E, as an evaluation of algorithm uncertainty and the performance. We investigate a class of filtering algorithms that include the classic common filter in linear settings, the deterministic gain common filter, and the extended common filter in nonlinear cases. Our method has proven to be applicable for both systems with Gaussian noises and non-Gaussian noises. In specific, we express the estimation error as a randomly weighted sum of history noises and the initial error. Then, by studying the magnitude and the dependency structure of the weights, we construct a surrogate error process whose even moments dominate those of the true estimation error. Therefore, we can use moment-based probability inequalities, such as Markov inequality and the Chernoff inequality. We apply this approach in an epidemic model with both Gaussian noise and Laplacian noise. Moreover, as we verify and compare different confidence intervals, it motivates the further stochastic comparison analysis between the distribution of the true estimation error and that of the surrogate. Thank you very much for your attention. If you are further interested in the details of our work, welcome to discuss with us during the interaction session or to take a look at our poster and our paper. Thank you.